Hello and welcome to NPTEL MOOC on Applied Electromagnetics for Engineers. I hope you have been finding these lectures useful. So far we have considered only the case of lossless transmission lines, which although might be a very good approximation to some cases, especially at high frequency transmission lines, they are not really the most general transmission lines that one can think of, nor they are quite practical at mid frequency and low frequency conditions, where the line resistance and the dielectric loss of the dielectric that fills the transmission line medium has been neglected. Of course, in a real world dielectrics are not perfect, there will be a certain amount of leakage through the dielectric which manifests as a leakage current, and this leakage current flows between the two conductors that are used for the transmission line and constitutes a leakage current. Okay. And this leakage current can be modeled by assuming that the dielectric behaves not just as an ideal capacitor, but also as a small amount of conductance to it. Okay. So, this conductance times the voltage difference between the two conductors of the transmission line will create the leakage current being G into V. Similarly, when I consider a transmission line made out of a conductor, of course, if I assume a superconductor, then the line resistance can be neglected, but in any ordinary metal conductor that I find, for example, a copper or a gold or aluminum wires or whatever those wires that I consider, they all have a certain amount of resistance associated with it. This resistance is also because of the material properties, okay, as well as by the guided nature of the electromagnetic waves that are propagating. That evaluation of the resistance as well as the conductance, I will leave it for a later case where we have thoroughly understood Maxwell's equations, and the resistance of these conductors goes by the name of skin effect, and evaluating skin effect is a major topic that we will later on consider after we have looked at Maxwell's equations. However, the circuit model of the transmission line that we were considering, the distributed circuit model in which we had modeled the series inductance and the shunt capacitance, can be augmented a little bit in order to consider these non-ideal effects of series resistance and the shunt conductance. So, if I go back to the unit cell, that is the kind of one infinitesimal length that I consider in deriving the voltage and current equations, okay, that unit cell will now have in the series side will have the resistance as well as the inductance, and in the shunt side will have a capacitance and a certain amount of shunt conductance. Instead of working in a general Z and T domain, we will specialize to the frequency domain behavior, which means that all my sources are oscillating at a particular oscillating frequency omega, and therefore I can replace the impedance of an inductor and the shunt susceptance of a capacitor by their equivalent frequency domain reactance values. You must remember, or you may recall, that if I consider an inductor which is taking up a voltage or having a current through it at a particular frequency omega, the reactance that it presents will be omega L. In the complex phasor notation, this corresponds to j omega L, and you remember that this j omega is nothing but del by del t, and it kind of makes sense, right, because the voltage across an inductor will be L di by dt, and this del by del t term can be replaced by j omega, and therefore j omega into L will be the complex reactance or the impedance of an inductor. Similarly, for the capacitor, you can see that this would be equal to 1 by j omega c, that would be the equivalent reactance of a capacitor. So, the unit length or the unit cell of the transmission line, if you want to say so, will now be different in that it will include the series resistance and the inductance of j omega L reactance, and in the shunt case will include a capacitance of j omega c, and then the admittance or the conductance of this particular dielectric loss that is being modeled will be denoted by G. So, this happens to be one unit cell. Of course, in the adjoining unit cell you will again have an R, you will have j omega L, and then you will have capacitor and conductor and so on and so forth. This would never end. As before, R and G are parameters, okay. R will be measured in ohms per meter and G is measured in Siemens per meter, which is the unit of conductance, and these are per unit length quantities. Together R, G, L and C are called as primary constants of a transmission line, sometimes also called as distributed constants of a transmission line. As before, evaluating them requires knowledge of electromagnetic theory, which will come after this particular transmission line chapter. Okay. So, we need to know Maxwell's equations to find R, G, L, C, but for now we will assume that someone else has calculated this R, G and L and C and they have given it to us, and our idea would be to try and find out what would be the voltages and currents. To that effect, again I consider two planes, one at Z and the other plane at Z plus delta Z. Okay. So, I consider one more plane at Z plus delta Z and find out the voltage phasor here, which is V of Z. The voltage phasor here will be V of Z plus delta Z. There will be some current which would be the current phasor IZ, and the current here would be I prime Z plus delta Z. I can go through the derivation again, but I am going to leave this as a small exercise to you to show that the way the voltage phasor changes along the transmission line, the voltage difference between V of Z here and V of Z plus delta Z over here will be given by R I phasor plus J omega L into I phasor. This part is familiar to you. This is actually coming from del by del T, L del by del T of I, okay, whereas this R into I is simply the ohmic drop across this resistance R. Similarly, we have another equation for the current phasor, which is di by dz, and that would be given by G into V, G being the conductance, conductance into voltage will be the current, plus J omega C into V bar. Sorry, there is a minus sign all over the place which I forgot. Okay. So, there will be a minus sign here. I can even simplify this one and also confuse you a little bit by writing this as minus Z into I and writing this as minus Y into V, where clearly Z is given by R plus J omega L, and this is called as the series impedance per unit length, and Y is the admittance, which is series admittance per unit length given by G plus J omega C. There are a lot of Z's going around. One Z that is there is the direction of propagation. This capital Z is the series impedance. We also use Z to denote the impedance at any particular line of the transmission line. So, you have to be a little bit careful in understanding these notations. Okay. Usually the context in which these symbols are used makes it very clear as to what quantity we are talking about. Coming back to this set of equations, these are, thanks to the phasor notation, they are ordinary differential equations and they can be quite easily solved. For example, I can solve for the voltage V by differentiating this expression here. If I differentiate the first expression for the voltage, I get d square V by dz square, and that would be equal to minus Z. I am assuming that Z is independent of Z, right. This is a uniform lossless transmission line, into di bar by dz, but di bar by dz is nothing but minus Y into V. So, if you actually solve this, I mean if you make a second order differential equation for this, you will end up with an equation which says d square V phasor by dz square, how the voltage is changing along the transmission line, is given by Zy into V. Okay. You can substitute for Z into Y, and it turns out that this would be one complex number multiplied by another complex number. Therefore, I can write this as some gamma square into V, where gamma will be a complex number called as, gamma is called as the complex propagation constant. Okay. The complex propagation constant will have two terms. I can always write a complex number as some real number and an imaginary number. This real number is called as the attenuation constant or attenuation coefficient, and this would be the phase constant or the phase coefficient. Again, the equation that we have considered is d square V by dz square is equal to gamma square into V. The solution of this equation will be in the form of e to the power plus or minus gamma into z. By substituting for gamma as alpha plus j beta, you will see that the solutions would be of the form e to the power plus or minus alpha z, e to the power plus or minus j beta z. For a wave that is propagating in the forward direction, if I choose a minus sign here the voltage phasor can be considered as e power minus alpha z e to the power minus j beta z. The phase continuously gets delayed, that is the wave gets delayed as it propagates along the transmission line. In addition, the amplitude of the wave also decays. The rate at which this amplitude decays is given by 1 by alpha, or rather alpha, it is the rate at which this is given by the amplitude decay, and this minus beta z will tell you that the voltage wave is actually harmonically oscillating. So, if you look at the voltage on the transmission line, here the voltage along the line would change something like this. Okay. So, along the line you would see that the amplitude continuously decays and the voltage is actually still oscillating at an appropriate frequency and the phase constant of beta. If you start at one particular point on the transmission line and then move a distance of 1 by alpha, you know that the value would have dropped. The value of the voltage at this point would be just e to the power minus 1 times whatever the voltage that we started out here. Okay. This is the voltage that we started out at this point times e power minus 1, which is about 0.36 times the value would have dropped. If I go to another 1 by alpha, the voltage would have dropped by 0.36 square. If I go 4 times, the value would be dropped to 0.364 of the initial value, and 0.364 is approximately 0.01. So, you can say that the voltage after 4 1 by alpha times of propagation length would have dropped by 99% of the original value, which means that the remaining value is almost 0, right. If V0 is reasonably okay, the voltage at this point after 4 into 1 by alpha will be very, very small compared to the voltage amplitude at the initial or whatever point along the z that you consider. This 1 by alpha therefore is called as the characteristic or the attenuation length of the transmission line, and it is given by 1 by alpha. Alpha is a unit that is measured in Nepper per meter. Okay. Alpha is the attenuation constant that is measured in Nepper per meter, but in practice this is also given in dB per meter. The conversion from Nepper to dB, I will leave this as an exercise to you. In the textbook it is very quite clearly given to you, and I would refer you to textbook out there. Okay. To summarize what we just did, we considered a more general transmission line wherein we had R, L, C and G, all terms related to the transmission line were present. It resulted in the transmission line having a unit cell with a series impedance and conductance or the admittance of Y. Y was given by G plus j omega C, Z is R plus j omega L, gamma is equal to, or rather gamma square was Z into Y, which is R plus j omega L into G plus j omega C. The complex propagation constant gamma, which is alpha plus j beta, is given by square root of R plus j omega L into G plus j omega C. The solutions were that we considered for the positive travelling wave was e to the power minus alpha z, e power minus j beta z. If I consider z to be negative, that is for the wave that is propagating in the left or the backward direction, these signs can be reversed. I can have e power alpha z, but please note that z has to be negative for this, and then I will have e power j beta z. If z is still positive in your coordinate system, you cannot have, so you can still consider it to be e power alpha z, except that the amplitude here would be larger and the amplitude actually drops as you go along z. So, you have to carefully consider which coordinate system that you are using. We frequently do not really worry about these backward forward things because the context kind of makes it clear and the signs are taken appropriately as we would like it. The attenuation length or the characteristic length L alpha is given by 1 by alpha, and you can kind of be pretty much sure that by 4 times 1 by alpha, most of the voltage wave would have dropped to very small amount of the initial voltage. So, it would have dropped to very small amount of the initial voltage. There is one other thing that we have not talked about for this transmission line, and that happens to be the characteristic impedance. To get to the characteristic impedance, let us we first write V as V0 plus e power minus gamma z plus V0 minus e power gamma z, right. So, this is how the total voltage phasor can be written, and the voltage phasor, if you differentiate with respect to z, what you end up will be minus gamma V0 plus e power minus gamma z plus gamma V0 minus e power gamma z, but this is nothing but minus z into I phasor, right. So, this is nothing but minus z into I phasor. I can write by taking out this z onto the left hand side and rearranging the equation. I can write I to be equal to minus gamma divided by minus z. So, minus and minus signs cancel with each other, giving you gamma by z and V0 plus e power minus gamma z, and then minus gamma by z V0 minus e power gamma z. I can consider this as the amplitude I0 plus, I consider this as the amplitude I0 minus, okay, and then take the ratio of V0 plus to I0 plus. This ratio turns out to be z by gamma. Z is nothing but r plus j omega L, gamma is r plus j omega L into g plus j omega c, okay, under root, and this would be equal to square root of r plus j omega L divided by g plus j omega c. You can actually get the same relationship by taking minus V0 minus divided by I0 minus, which will again give you gamma by z, or and as the admittance and the impedance as z by gamma. In contrast to the lossless case, where Z0 for the lossless case was purely real quantity L by C, this time you see that in this particular case, which can be considered as a more general transmission line case, the characteristic impedance happens to be complex, right. So, this characteristic impedance being complex means that not only the voltage value over at one particular Z will be different from the voltage at this point, right, in terms of phase, but then the amplitude also will be different. Usually the amplitude kind of decays, therefore, the voltage as you start propagating along the transmission line near towards the load will not only reduce in amplitude, but will also change in phase. Okay. These also introduce couple of additional factors that we will consider in the next few modules. So, we stop at this point, okay, and we consider a few problem solving in the next session, and also address a couple of misconceptions that normally is found when we are discussing transmission lines. Thank you very much.